Hello everyone, my name is Jawad Rafi'i Asl. I'm going to present a paper that is called An Efficient Deep Learning Model for Intrusion Classification and Prediction in 5G and IoT Networks. This paper has been done by 5 researchers as mentioned in here in 2019. Okay, as outlined, I will focus on the motivation behind the work and problem definition, then provide a general problem solution that is NIDS. Meanwhile, the proposed approach will be investigated and experimental results will verify the performance of the approach. Finally, the conclusion will concentrate on the future works. Nowadays, new internet-based technologies has been appeared that utilize wireless networks to provide necessary services for the customers. IoT or Internet of Things is one of those technologies. IoT is the way of connecting the physical objects through the internet to other devices. The things in IoT are defined as objects with a built-in sensor having IP addresses with the ability to collect and transfer the data over the internet. Moreover, 5G as the fifth generation mobile network is a new global wireless standard after 1G, 2G, 3G, and 4G networks. 5G wireless technology is meant to deliver higher multi-gigabit per second peak data speeds, ultra-low latency, more reliability, massive network capacity, increased availability, and a more uniform user experience to more users. Both of the mentioned new technologies are designed based on 802.11 wireless protocol. 802.11 protocol refers to a family of specifications developed by the IEEE for wireless LAN or VLAN technology. This protocol specifies an over-the-air interface between a wireless client and a base station or between two wireless clients. There are several specifications in the 802.11 family. Some of them is used for 5G technology, the others are used for IoT technology. As technology becomes more and more integrated, security of these systems over wireless networks is becoming more important. Nowadays, cyber attacks has increased by an alarming rate as the Internet of Things or IoT and 5G technologies are widely used to provide efficient services. This drove to an increase in research for more secure online systems, especially in the intrusion detection systems. As a general solution, a network-based intrusion detection system or NIDS are used to detect network-borne attacks such as flooding, denial of service attacks or malwares that are operating within the system. The NIDS monitors network traffic and helps to detect malicious activities by identifying suspicious patterns in the incoming packets. As shown here, the NIDS sniffs the internal interface of the firewall in read-only mode and send the alert to a NIDS management server via a different read and write network interface. This slide depicts the general architecture of the proposed approach in the paper. As shown in here, two types of uh, accesses can be introduced to a system. A desire connection from a genuine user node that need to be considered as normal traffic, uh, or undesired connection from an attacker node that should be detected as an unauthorized traffic. The proposed approach is able to handle three main types of flooding, injection, and impersonation attacks. All of these attacks will be investigated in the next slide. This approach concentrate on exploring low latency models while maintaining high accuracy by proposing a deep auto-encoded neural network framework for effective intrusion detection. So the NIDS using deep learning did alleviate the need of feature selection or feature engineering during the detection process and so reduce the latency. As mentioned, three main types of attacks are managed by the introduced methods. The first is flooding, that is designed to cause an interruption of services for a specific server by flooding it with large quantities of useless traffic or external communication requests. This flooding effect can be observed in numbers of ways. For example, slow response of the server, slow networks performance, unavailability of software or web page. The second one for the impersonation attack, the clients unknowingly connect to attackers under the pretext that they are connected to a genuine access point. Once a client is connected, an attacker eavesdrops on its communication to hijack client communication and redirect client to malicious website and steal the credential of the clients. In the injection attack, the attacker uses existent vulnerabilities in the applications to inject a code or script for execution that exceeds the expected input to the system requested. In the last column, for each main categories, there are different subcategories of attacks. Most of them is related to the flooding or denial of the service type. However, the proposed approach is able to detect only the main categories in here. In order to evaluate the proposed approach, AGN Wi-Fi intrusion dataset or AVID dataset was publicly released as a comprehensive 802.11 network dataset that contain real traces of both normal and intrusive wireless LAN traffic. Each record in the dataset is represented as a vector of 156 attributes, with the last attribute being classed. Each record is composed mainly by MAC information. All attributes in the dataset have numeric or nominal values, and the scale of the attributes on the dataset are heavily imbalanced. On the other hand, there are two types of AVID dataset. The first type, named CLS, has 4 target classes, whereas the second names ATK has 17 target classes. The 17 classes of the ATK dataset belongs to the 4 attacks category in the CLS dataset. Here, the table shows the ATK version of AVID dataset that includes 16 specific type of different attacks. These 16 types can be categorized to 3 main categories of attacks that are flooding, injection, and impersonation. The last category is the normal traffic in both versions of the AVID dataset. Here, the pre-processing step of the proposed idea is investigated. Before to be able to employ deep learning technique, the dataset records needs to be pre-processed and converted to a suitable format for training and test steps. In training and test dataset, there is a total number of 2,371,281 instance labeled dataset records. 20% of the entire dataset was used as a test dataset, and the remaining 80% of the dataset was used for training and validation purpose. The data contained in the AVID dataset are diverse. The data contained in the AVID dataset are diverse in value, discrete, continuous, and symbolic, with the flexible value range. So, various pre-processing operations are performed to make dataset more appropriate for training aims. The method has replaced a missing value with zeros, drop out the feature with duplicate information, and the columns with constant values, as they contain no class-wise distinctions and information. The method has also applied log encoding in the large numerical features such as source byte, destination bytes, and duration feature to avoid any kind of biasing on the training due to their large value. Then the method performs a standard scalar function as a normalization operation on the feature vectors of the dataset. As a result, the total number of input dimensions is 36 after performing the above mentioned steps, and the output dimension is 4, that is related to 3 attack classes plus 1 normal classes. Before concentrating on the proposed deep neural network-based approach, it is necessary to take some important points into consideration. The approach considers 2 main factors during implementation of the NIDS for the wireless realms. At first, the system should provide extremely low on false positive alerts due to the large volume of data. So a false positive rate of 1% may generate a great number of false alerts on the daily basis. Second, it should be highly adaptive to drastic network behavioral change because of new events and natural changes in equipment. The system should also be able to detect novel attacks as wireless technologies change, and new vulnerabilities should be added into system. 2 main functional stages are employed in the proposed model. An encoder that operates based on and unsupervised pre-training on the data to provide compressed and less noisy representation of the input space, and a dense neural network function as a supervised classifier for the experimental intrusion detection scenario. Both of these steps will be investigated in the next slides. Here, the diagram illustrates the workflow and the proposed deep model architecture for the intrusion detection system. After dividing the dataset into two training and test subsets and doing the pre-processing step, the extracted features are fed into the autoencoder. An autoencoder is a type of artificial neural network used to learn efficient data representation in an unsupervised manner. The encoder part of the autoencoder aims to compress input data into a low dimension representation, and there is a decoder part that reconstructs the input data based on the low dimension representation generated by the encoder. A set of compressed and robust feature is built at the end of this step. The main objective of training such autoencoder is to find the optimal parameters to minimize the difference between the input and the reconstructed output over whole training set as shown in this equation. After autoencoder layer, a three-layer dense neural network is employed by using autoencoder output as its input. This task is retrained in a supervised manner with the class labels and the input feature given to the classifier. The method has used a softmax activation layer as an output layer. This layer calculates the loss between the predicted value and the true values, and the weights in the network are fine-tuned based according to this loss through the backpropagation operation. However, in the test phase, the softmax layer outputs the probability of the predicted categories that can be used for the performance calculation. This slide shows the algorithm employed by the proposed approach for training the model. As an input, the model has training dataset and the number of layers. For each L from 1 to the number of layers, it initializes the weights and bias for autoencoder. In the encoding layer, the model calculates the encoding or hidden representation of the data. In the decoding layer, it calculates the original data from the hidden representation data, and then it calculates the loss function between the original data and reconstructed data until a specific threshold will be satisfied by the value of loss. After that, a dense neural network used as a supervised classifier with a softmax activation in order to predict the output result. So in here, the method initializes the weights and bias at the supervised layer, and then calculate the label for each sample xn of the training dataset, and then apply batch normalization and dropout for speeding up the calculation, and then based on the loss function, it performs back propagation in the supervised manner to fine-tune the parameters of all layers. So now it's time to investigate the model evaluation using different experiments. This diagram plots the network training process for 100 iterations. During the training, the method has used additional technologies such as dropout and batch normalization to avoid the overfitting problem and also to speed up the training process. So the proposed algorithm achieves approximately 99% accuracy training set in only 20 iterations, which is 4 times faster if no dropout and batch normalization was employed. This figure presents the confusion matrix for the proposed model when evaluated with the test dataset. The row in this matrix correspond to the predicted class, and the columns correspond to the true classes. The diagonal cells in the confusion matrix correspond to observations that are correctly classified, and the off-diagonal cells correspond to incorrectly classified observation. Both the number and the number of observation and the percentage of total number of observation are shown in each set. The column on the far right of the plot shows the percentage of all the examples predicted to belong to each class that are correctly or incorrectly classified. The model approximately obtained a true positive rate of above 99% for all of the attack categories and normal connection. For flooding attack, there were only 1.2% false prediction that made by the model. For the injection and impersonation type attacks, it is even lower as 0.1% and 0.9% respectively. On the other hand, there were several neural networks and deep learning-based methods with variable accuracy for the underrepresented attack classes. This table summarizes the class-wise true, positive, and the overall accuracy of the proposed model with some concurrent deep learning methods. The introduced at the last row, in the last row, the introduced approach outperformed previous related works in terms of class-wise, true positive, and overall accuracy. Okay. As conclusion, cyber threats have become a prime concern for information security. NIDS is one of the security mechanisms used to guard these applications against attacks. This research has applied a deep network intrusion detection model and evaluate the algorithm with the benchmark AVID dataset. The result shows an excellent performance. The The result shows an excellent performance with an overall detection accuracy of 99.9% for flooding, injection, and impersonation type of attacks. Future models will cover a broader range of attacks, respond in real time, and update itself over time. Also, future works improve the detection accuracy to reduce the rate of false negative and false positive in attack detection system to improve the system performance. Thank you so much for your attention. If you have any question, just write the post under the video. I will answer your question. Thank you so much.